Okay, so we put together some few experiments, 5 or 6 experiments. The idea is to show like how a simple thing can, hold in it some deeper science. So that's the idea. We haven't put together any fancy, costly experiments. Like in fluid mech, you have an amazing range of experiments. So, like just the simplest thing, like if you have an incredibly fast camera and you just drop a drop of milk in water and you can see how it crowns. You can see amazing things just by recording it very fast, things that you can't see with the naked eye. So there are many fancy things like that, which we're not doing. We're doing very simple things and we are here to explain the physics behind it. So that's the basic idea for today. So Prateek will start. And feel free to ask questions. And for some of the experiments, you may want to come in front and see. Like reversibility also, it's good for them to come in front. Yeah, okay. Come in front and see. When he's starting the experiment, all of you can come here.
So, okay. Okay, so will you do this? Okay. Hello, everyone. So we will start off with the first experiment of the day. That is to demonstrate reversibility in Stokesian flows. So what are Stokesian flows? So as Rama talked about in her lectures, this is the non-dimensionalized Navier-Stokes equation. And the RE is the Reynolds number that I have just defined using some characteristic velocity scale U, some characteristic length scale L, and the kinematic viscosity of the fluid nu. Now, in the limit of RE going to 0, no, I should not say limit. In fact, RE exactly 0, the Navier-Stokes equation reduced to Stokes equations, which is given by this term, like minus grad P plus del square U is equal to 0. Now, if you just focus on this equation now, and so now we are trying to see if these equations are time reversible or not. So to check the time reversibility, what I do is okay. So you are saying I should retain just this term? Huh?
Yeah. So okay. We will have a different scaling for that.
Right.
So put like the Struve number times the Reynolds number.
Okay.
Can you write bigger? They have to see it.
Okay. Okay.
Like the first term by a Struve number and the second term by a Reynolds in the top equation.
You mean this?
First term by a Struve number.
Okay. 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 I'll just
first term alone.
First. Okay. You are saying that. Okay.
Yes.
Right. So I'll just so now we take the limit of Reynolds number going to 0. And so physically speaking, this kind of limit is possible for very viscous flows. For example, honey, glycerol, silicone oil, all these kind of fluids. So now if we just focus on the Stokes equation, so we want to investigate about the time reversibility of this equation. So to check that, I just replace T with minus T. And in doing so, I'll have to replace U with minus U and P with minus P. U is the velocity field and P is the pressure field here. So if you make these transformations, what will you get here? So this term, you will get there will be a minus sign here from grad P, and there will be a minus sign here that will come from del square U, and that will be equal to Struve times dou U dou T. So what this tells you is, so in the limit of, so right now these equations are irreversible, as you can see. So for these equations to be reversible, what should have happened is these equations should have been exactly equal to these equations. But you can see we have this annoying minus sign here. So, so very slowly. Unsteady. So Struhel number basically is the ratio of the time scales, like the time scale of the external imposed flow force versus the inherent time scale of the system. So if we assume that both the time the flow is very slow, as Rama mentioned, then you can just ignore this term, and what you will land is with this equation, minus grad p plus del square u equals 0. So these are called the Stokes equations, and these are time reversible. So these are time reversible. Okay. So our experiment here is, it is a Taylor-Couette apparatus that will demonstrate this time reversibility. This experiment was first done by G.I. Taylor way back in the 1960s, and we will now proceed along those lines. So Iqbal here will do the experiment.
Or if you can see from there, you can stay there. It's your choice.
So first I'm going to pour it, otherwise it may. Okay, so first of all, I need to put glycerol and fill the half of the cylinder.
So remember that glycerol is a very viscous fluid. So by the choice of that fluid, we are automatically keeping the flow very slow, we will automatically go to the Stokes regime.
You can see how long it's taking to pour itself.
Okay. So now I'm going to put 2 lines of this dye here, and then let's see what happens. Okay.
You want to say something?
Yeah. Okay. So now I am going to rotate this very slowly, as slow as possible.
Because he has to make the du by dt term 0. That's why he's rotating very, very slow.
So the system should not be unsteady and the fluid is highly viscous. So let's see what happens under these conditions. So as you can see, the lines, the initial lines, they are now smearing out. Okay. You will do one full rotation, right? One full rotation.
Pi.
Okay. Okay, bye.
Okay. So I have rotated this by angle of pi. Now I will rotate it in reverse direction. Okay. Okay. Vibration. Perfect. Yeah. So you see, we got again the lines, straight lines. So.
Okay. So yeah, as Iqbal very nicely demonstrated, so as long as you keep the entire process slow, it is possible to achieve the initial conditions that you started off from. And so one thing to note here is that you must have noticed that once Iqbal stopped rotating the inner cylinder, the fluid also stopped rotating, right? So why that happened is because there is no inertia in Stokes equations, right? So because there is no inertia in Stokes equations, the fluid will move only when the boundary moves. And as soon as the boundary comes to a stop, the fluid will also stop. So these two things have been demonstrated by this experiment. So any questions? Acha. So in the experiment, there is no assumption as you can see, if you just focus on this dye again, there is a slight amount of diffusion. Is it visible? So as you can see here, initially we started off with very nice lines, but you can see there is still diffusion. So mass diffusion has occurred, but yeah, you are correct that it should be low mass diffusion in this case, which I guess because of high viscosity, it is.
Yeah, so Pratik is right that we cannot make an assumption for the experiment. The experiment does what it does. And indeed, like there is a small amount of diffusion that you see there. But the point is that, remember we talked about mass diffusivity and momentum diffusivity and everything on that day, on the first day. So like in a fluid, you should, but this is like one liquid in another, so the diffusivity is not that small. In fact, Iqbal, you have put the dye in glycerol itself, right?
Yeah.
So it's in fact the same fluid, and that's why it's diffusing.
Right. So if you calculate the relevant non-dimensional number, which is the Reynolds number in this case, it will turn out to be very small. So the left hand side of this equation will not match. So these are the terms that characterize the inertia of the fluid, right? So if the Reynolds number turns out to be very small, inertia is negligible in comparison to these viscous forces. So right hand side are the viscous forces. So does that answer your question?
And one more thing to add is that the Reynolds is very small, so the nonlinear term goes off, and the Reynolds in fact is 0. And whereas the Struhal is not 0. He had to move it, right? Like he had to move it, but very slowly. So that's why I thought it's better we call it by two different names, because you're scaling it slightly differently. But you could also call both of them the Reynolds number as is normally done, and like, get a steady Stokes equation. Any other thoughts, questions, anything? Any comments?
Different from the coed flow in that we have a silent rotating. Is it different from coed flow or?
So this is in fact a Taylor-Coed setup.
Okay.
So yeah, so this is like a circular. You must be talking about the flat plate Coed flow.
Cylindrical thing.
So this is a Taylor-Coed flow. That is. It's much like history.
Sejal, this question is not clear.
I don't understand. What is retentivity?
Can you explain the question? Okay, you can continue. Maybe she can put the question.
Okay, I guess.
Yeah, so this thing, once we take it forward and we get it back, there's some amount of spread.
Right.
So one thing which you're saying account for the spread is the diffusivity.
The mass diffusion.
Yeah. But suppose if I do the same process fast and come back.
If you do this process fast,
yeah,
then we cannot, equation wise, we cannot drop the inertia terms anymore.
Okay.
So the process will not be reversible anymore in the first place.
So
okay. Iqbal will not be happy, but okay. Do it fast, Iqbal. See the irreversibility also.
No, that's okay. They're showing it.
They're showing it.
Yeah, just do it very fast. You have to move it very fast because it's very viscous.
Oh, it still came back. Yeah. It is so viscous, it still came back. Yeah. I think it has to.
Do it even more
Let me try again.
नहीं अभी थोड़ा see नहीं right now it has spread a bit more थोड़ा सा a bit more yeah.
Next time we'll do some.
No, I think you can see that okay here it's coming up, yeah.
water or something.
Yeah. Yeah. It is so viscous, it's still coming.
You see that whatever you do, Reynolds is slow in
Mhm.
this.
Right. Is that clear?
So how much you do this rotation also in some sense decides the spread. Now, all I'm wondering is, suppose you only have the spread information, what all can you measure?
Spread information meaning how much this line has spread, like.
Yeah. Based on that, you can measure some properties of liquid or the. Yeah.
That way. Spread out.
One is clearly the diffusivity and all of that, but that should be.
You can get some estimate of the Reynolds by moving it fast if you can neglect diffusivity.
But again, would that account for how further you moved, say theta versus
Yeah.
2 theta?
It will matter how many times, how far you go.
See, one thing is in this setup, this gap width, you see, right, there's a gap where we're putting the ink and the fluid. This gap width is quite small. So if we try to go to a large number of rotations, by that time, the ink will start sticking to the walls and all, and our experiment will be spoiled. So if we had like a larger gap width, then we can do what you are saying. We can rotate it for long and then come back. But experimentally, it has been shown that you rotate a lot of times and come back, you will get back those lines and all, as long as a Reynolds number is small.
What is in the chart? Otherwise, we can move on to the next.
Okay.
Just to repeat, this is just a single cylinder setup. What if I had two opposite rotating cylinders, and would you be able to account for the same, or?
Two opposite rotating cylinders, like how? How will you arrange them?
Just one next to another, and the same gap width what we have between the cylinder and the beaker. Just in a situation when you have.
So you're asking if it will still be reversible.
Yep.
So yeah, see that concept still holds regardless of what is the geometry, right? Like as long as the fluid is viscous and you are sharing it very slowly,
Okay.
No matter, you can put 4 Taylor-Coed setups or something, it should still work.
So regardless of how the flow is being altered, you'll be able to reverse it.
You will be able to. So it's like on a fundamental level, as long as Reynolds number is slow, we did not make any claims about geometry there, right? Like in the equations, if we just focus on equations, there is no assumption on what is the geometry. Just the Reynolds number should be small and Struhel number should be small, both of those. Oh, chat, man.
So this length scale in Reynolds number is the gapping.
You can take that. The gap width is the length scale. I think we can move on with the next experiment. Achha.
Any questions?
Okay.
You had a die at the interface. You see something like Helmholtz instability. I mean, I don't know.
That will be the
instabilities. Can you see the instability?
shearing? That will be Kelvin Helmholtz only, right? Two
The viscosity is
very high.
Oh, nothing happens because, okay.
Yeah. But if you have a viscosity which is a function of space, then you have to put it into that equation and you have to rewrite to see if it is going to be still reversible or not.
Right.
Let me open the chat.
Somebody can read it.
Yes. Now, can you open the chat?
Yes.
We get the same result. After same
In the next one, we'll take care of maybe the last.
Yeah. No, so Kanya is asking this. Will we get the same result after many full rotations?
Yes.
So yeah, that the result will be the same. Yeah. As long as it is done slowly enough, it will be the same. The ink did not return to its page. It had to be displaced further to the right. Was it?
So she's saying that it wasn't.
Hmm.
She's saying that he went out by pi, but he came back by more than pi. I don't know whether.
Is that? Just do it again. Okay, this slowly. Yeah. Okay. That is fine. I think he is coming back. All right.
Pi, right?
It's a actually it's pi. We just tested it again. It is pi only. Yeah.
Sir, I had one question about the fact you said that it doesn't depend on geometry, but like if we replaced it with something like a cubicle, I want the boundary, like won't it be too sharp for the fluid to actually?
No, as long as it is not, well, it should not stick to the boundaries, right? Like wire is, it should not stick to the boundaries. Sharp edge, smooth edge, whatever edge. So that's what I think, Rama.
Yeah.
It should be fine. Right?
Yeah, it should always work.
Yeah, it should always work.
And Nishant has a question. You can answer.
Is this reversibility the reason? Yeah, that is correct. So when you say low RE, like you should really say RE is equal to 0. That is important. So yeah, because of reversibility, the streamlines will be symmetric for flow past a sphere. That's good. Yeah, so actually, yeah, I don't think it is reversible thermodynamically. It is only kinematically it's reversible. Like there is still viscous dissipation, because remember it's a viscosity dominated flow. So viscous dissipation is happening. Therefore, entropy of the system is still increasing. That is correct.
So this is in context of the cube question that he asked. Suppose if I have a very sharp flat plate and I'm moving it through a very viscous fluid, won't that like say if the plate is extremely sharp at the edge, doesn't matter how slow I move, the velocity at the edge of the fluid will be very large, right? So locally the Reynolds number will be large at that point, and that would break the reversibility.
If it's very sharp.
So like if
Okay.
See, even if it's very sharp, like the velocity gradient can become large, but the velocity will never become large anywhere. So long as things are moving slowly, there'll be no large velocity anywhere. Okay, looks like we're done with this, so we can move on. But that doesn't mean that if you have further questions you can't ask, you can always ask Pratik. Yeah, ask.
Yeah, you can make a spherical blob. See, we put lines because we don't have much space there in the gap. If the gap was bigger, we could have put a spherical blob and we could have done the same process slowly.
So such experiments are already designed, or?
Yeah, so like the first was demonstrated in the 1960s by G.I. Taylor. And since then, yeah, these experiments have been done. So this reversibility has been established experimentally also.
Results were all similar.
Yeah, they were similar. In fact, the original experiment was done with a blob of fluid only. It's like a spherical blob, what you are saying. It was not a straight line that way. So you can try whatever shape and all, it should be reversible. Yeah.
Can you hear me? I guess so. Okay. The next problem is not as pretty as it is visually, but it's intriguing when you think about the problem. And the problem can be seen there. It's basically a ghada which has a water inside, and the ghada is made of clay. And at least we did. I don't know how many of you had that you put water in ghada in summer and it cools down and you drink the cold water. And the physical explanation behind this in our high school, some of us studied, at least I remember studying, but I then forgot until Rama told me. But nevertheless, the reason it happens is because water sweeps out of the porous medium, which is clay, comes at the boundary, then evaporates. And as it evaporates, it takes away latent heat from the inside water, from the body itself, and it cools the body, similar to how we sweat and cool ourselves during the summer. So the question is, therefore, can we understand how temperature decreases and how the concentration of water decreases? What happens at the boundary? So we first start by doing some rough calculations to see if our physics is correct. So what we claim is, okay. So this is our claim, and mathematically it comes down to L delta L equals to ms delta T, where this is heat of evaporation This is again water lost. This is the net water inside. Of course, this will change, but as Iqbal gives me the data, the amount of water lost is very small compared to the total water that was originally inside. So we can take that to be the constant. Specific heat of water. And temperature change. Which means that I can easily pull out del T as specific heat of water. Okay, that's a bit consistent. All right. So it's a simple claim which I'm going to make. Given that we assume around room temperature the density of water is constant, we can replace this by volume. The volume of water that has been depleted due to evaporation divided by the total volume of water that is, because it's easier to measure volume than measure mass. Okay, so Iqbal tells me that there was a 35 milliliter of water which was depleted, and he put in 3 liters of water. So this is delta M, this is our M. Again, 35 milliliters is very small compared to 3 milliliters, so 3 liters, sorry. So it's effectively constant. Yeah, that was around 24 to 30 hours. Again, the story is to write down, check whether our delta T is matching. So delta T was observed was around 10 degree in centigrade. So the delta T we get, does anyone here remembers specific heat and latent heat of evaporation of water? Okay. If anyone remembers, speak up. I'll be really impressed. Okay, no Googling. Okay.
Specific heat is 40 to 100 joules.
Specific heat is 40 to 100 exactly in SI. Okay.
And I think latent heat should be 3.36 into 10 power 5.
In SI, I'm not writing the units at SI. Yeah. L is what?
3.36 into 10 power 5.
3.3. Okay, I think you are looking at this at 100 degree Kelvin centigrade. We need to look at it 27 degree centigrade. And because I Googled earlier, I know that this is 10 to the power 6. Which makes sense because if you, it's much larger than at 100 degree because at room temperature, if you manage to evaporate some water, you need to give it more heat, the same amount of water. All right, so if you plug in these values, this was 2 into 10 to the power 6 divided by 40 to 100. Let's try to guess the final result. This will be 70 and this will be 12. Great. And and this will cancel away and this will be the delta T. So delta T that we get is around 5 to 6. Around 6. And what Iqbal observed was delta T around 10 degree. Now the order is same, 6 to 10. So we didn't get 60, which means the physics is more or less correct, but the 10 degree is a bit of uncertainty. And that happened because 24 hours is a long time. The temperature of the atmosphere changes in 24 hours. And during the day, when Iqbal put in the water, it was hot. At night, it becomes colder. So therefore, the background temperature, yeah.
And also maybe there was wind, right?
Yeah, outside
like
there's
if it's
wind.
outside, there'll be wind.
But again, given that this gives us similar order of magnitude, we will go with this concept that whatever is evaporated decreases the temperature. Now the question becomes, how will we understand it? How will we understand the dependence of background temperature, the dependence of background humidity? How will we make use of that? And we will understand that by using the concepts that Rama described for a scenting flower. Remember, for a scenting flower, we wrote down an equation for concentration and studied it while the concentration at some point, C for all times at R equals to R0, was held constant. Here, the equations are similar. What happens outside this ghara is that temperature convects itself. If there is a temperature gradient, heat will flow. If there is a concentration gradient of water vapor will flow. So in this case as well, the equations are similar. I'll write down the equation for temperature. Q. But except there is a term called Q. The question is, what is Q and why is it here? So what happens at the boundary of the ghara, if I assume the sphere to be a straight line, I'm only plotting in R. And if this is the boundary of the ghara, which is R0, at the boundary of the ghara, things are evaporating. Water is coming out, evaporating, leaving away. So at the boundary of ghara, in addition to the thermal conduction, there is an extra heat that is decreasing the temperature. And that is this Q. Right. And now all we have to do is find out what the function for Q is. But because this Q only acts at the boundary and nowhere else, we introduce a delta function. This signifies that the heat, whatever heat that is going away from the boundary, and that thing only acts at R equals to R0. Right. So the question is, how do we find Q? What is exactly happening? So remember, we wrote down this equation. We will make use of exactly this equation. Instead, we will divide it by delta T. and study what happens at every incremental time steps. Because this is a time derivative equation, so Q has to be expressed in terms of time derivatives. So basically this in delta t going to 0 limit becomes dm dt equals to ms delta t by dt. Right? The question is we have to estimate this dm dt. To estimate this dm dt, m is the density, right, times, okay, let me write it this way. So over the entire ghada, whatever vapor density was there, if you look at the ghada inside, there was a vapor density, and whatever the current vapor density is now, the rate of change of vapor density is the vapor density that went away outside the ghada. It is the amount of vapor that was lost by the ghada. So this is the equation for dm dt, which we have now. And from this equation, concentration is linearly proportional to density. It just, you multiply it by the mass per mole and you get density. So I can instead of concentration, write the similar equation for rho, because it follows same diffusivity, same everything. And from this equation, I can replace 2b now, if anyone remembers Gauss theorem or Stokes theorem, I don't remember which one it is, I can write down this grad rho. This A is at the surface of the ghada, because we only have values at the surface of the ghada. We don't want to look at the inside of the ghada. And because we are assuming that the ghada is spherically symmetric, okay, probably you can't see here. We assume that symmetric. So there will be only term of grad rho. So grad rho times dA at the surface of the ghada simply becomes R naught. So we have our dm dt, which means we have our q. So we have our q, and if I write it down, but remember this q is related to this dt dt, so we also have to take care of this thing. And this thing, again, I can do a similar thing, the total temperature difference, Q dot, the total heat that went away, is equal to the total, let's write it this way only. Let me explain this. So K kappa dot grad T gives what is the Q dot at every specific point, right? Because in high school, if you remember, we studied the Newton's laws, which was kappa T2 minus T1 by B. If two plates are held at constant, there's a rod connecting between them with conductivity K. The Q dot was expressed as this. This is just the infinitesimal form of that equation only. So the Q dot that we have here is expressed by this. And again, we assume the ghada is spherically symmetric. The only term that remains is 4 pi r square kappa del T del R. So this is the Q dot that we calculated, multiplied with a L, of course. And therefore we can equate this. By the way, am I the only one who thinks that I'm just saying stuff and people are not understanding? Because if you're not understanding, feel free to point out. Yeah.
Up for questions.
Yeah. So any questions so far? Okay. That's not a very good sign. Yes. I think it's for the online participants.
So the question is, well, there should be Well, I think we are getting there. There should be there should be expression for area as well, right? Because the surface area will matter.
Yeah, which is 4 pi r square. So far, we are only dealing with the boundary conditions. We are interested in finding the Q, which is at the surface of the ghada.
Okay.
And that's where the area comes in, which is 4 pi r square.
Well, you are doing it, and I shouldn't ask it right now, but okay. Instead of, if we go for more complex shapes, which gives more surface area, we will be losing the delta T much fastly, right? So
yeah, this is now a one-dimensional delta function. You have to do a three-dimensional delta function accounting for the geometry, and Q will become much complicated. All this will hold true. I can't pull out this. I can't write down this surface integral as 4 pi r naught square.
Yeah, I mean, I'm thinking of it from a design point of view.
Yeah, exactly. This is not spherical at all.
Okay.
So the one thing I want to add is that there is a basic point behind this experiment. We chose just a thing. I mean, that thing is not really a sphere, but it's the closest thing.
I was not thinking about that.
I know. So it's a different point I'm saying.
Yeah.
So like this one is not really a sphere, but we got something close to a sphere so that we can do this analysis and the numbers won't be too wrong. That's the hope. But the idea basically is that, you have a simple thing like the heat equation and the mass equation that we derived on that day. And what he's trying to show is, look, even such a simple one, the boundary conditions can make the problem so much richer. So when we just write down the equations and we never talk about boundary conditions, we never focused on boundary conditions in the class. But this experiment does two things. One is it shows about the boundary conditions, which is what he's painstakingly developed for you. Like, how will you think about the boundary conditions and put the right ones? That's one thing. And the second thing is what happens when there is phase change. So in daily life itself, like phase can go from one to the other. And like maybe all of you can come and touch this thing and see if you're convinced it's wet outside. And like if it's porous, like can you answer why it's not, falling down as liquid water? Like why is it only reaching the surface and staying there? You can ask yourself those things, and maybe at the end you'll explain the temperatures also, right?
No.
Okay.
We'll just get an estimate.
So basically, Iqbal has put 3 thermometers there. One is right at 3 thermocouples. Yeah, you can tell where they are.
So I have 3 thermocouples. This one at the left is at the center of the ghada. Then this one is at the inside surface of the ghada. And this one is at the outside. So basically you see the temperature here is 22.4, cooler than the room temperature, which is, let's say, 22.9 or 23 now. Yeah, so I'm telling the room temperature is more than 22.9, let's say 23 or 24. Then this one, which is at the inside of the ghada, that is basically a little bit more than this temperature. But here, I mean, right now it was showing 22.7 because of the AC temperature, but this should be more than this. So coolest at the center, then inside a little bit cooler, and outside, of course, cooler than the atmosphere, but hotter than this too. And simultaneously, we also can get the data of, let's say, atmospheric humidity and temperature. Yeah.
So the coolest thing inside is because of its history also. So like how the outside temperature was over time where this ghada was kept. So otherwise it's conduction inside. So like whatever happens at the surface is the only thing that can get transmitted inside. And that's pure conduction inside.
All right.
But conduction is a slow process. So it will remember where it used to be and before he brought it to the AC room and so. Sorry, you can.
Yeah. All right. So now that we have a form for Q, we can again try to solve it.
There may be more questions.
Sorry?
We're asking for questions. That's where I stopped.
Sorry. Yeah. Any more questions? Yeah.
My question was about a spherical thing was, if I have to design a ghada tomorrow, I will go for one which will be more complex in shape, as in the surface area of the water will increase to the surface, I'm saying. Like, should that the approach I have if I have to design a ghada tomorrow? Say I have to do that.
That's one. The other one is you have to design it such that if you want to pour water from it, there is minimum spillage.
Yeah.
So if you look like ghada, in which a lot of water is kept, they have narrow necks. That's what minimizes spillage. So what you're saying is right. You have to maximize the surface area, but also minimize the spillage. That's not the only criteria that you
can
have.
add tap to that.
Yeah. That also works.
Right. Okay.
But then it's a different problem altogether. Tap has conduction in it. It's different material, and but okay. So it's a different problem. But the magic of this thing is, it's not magic. It's science first thing. The dominant thing will be this.
But one more question is there.
Yeah.
Okay, we haven't taken in consideration any property of clay here, but
no,
things will significantly change if we change it with something else, right?
Yeah.
Like if we add something to that clay, the property of like delta T will change.
No.
And we are not taking consideration of that. So
see,
are we missing something?
Clay, what clay does, it brings some water around, and that water should be enough, as we shall see, that water should be enough to give a saturation vapor concentration. As long as that's true, doesn't matter if you make the clay more or less porous by mixing some materials in it, everything will still hold. Okay, we'll see later. Okay, so we have Q, but what was the point? Yes. So the only difference from what Rama explained in class and what we have here is this Q thing, which is taking heat away apart from conduction, thermal conduction. And the question is, how do we get the Q? And the idea to get Q is similar to the quantitative idea we derived before, which is basically the amount of water that is lost in form of vapor takes away latent heat, and that changes the temperature, and that is going in this Q. So now we have an expression for Q in terms of rho. And this is how the temperature and the rho mix with each other. Because if you look at simply the equation itself, these two are different equations. They don't have any dependence. So one might ask, why should rho and temperature be related to each other? Why should one control the other? And this is through the Q itself, right? And that's how why all the derivation is still there. So now that you have Q, I'll just write an expression again. Yes. 5-10 minutes, it will be done. Now that we have Q, we can try and solve this equation. But the problem is it can't be solved analytically. And the reason is that we have missed another thing. Question is, I'm telling the amount of heat that will be taken away from the ghada will depend on the amount evaporated. But if the same amount of water is there at all times, same vapor density is there at all time at the surface of the ghada, it will keep on evaporating, and it will continue to decrease the temperature unless it turns ice. But in no circumstances, if you put in water here, you'll get ice. You can't get a free freezer out of here. And the reason for that is this saturation vapor density, which is so crucial, is a function of temperature. And it's a decreasing function of temperature. As temperature goes down, so does the saturation vapor density, unless it comes to a point that it can't evaporate and take away enough heat to cool it down any further. So what we will see, or what we will do now, is try to find out the steady state. Where will it go after a long time? And what happens at a steady state? In Rama's class, we did it a few times. Any ideas, guesses? The first thing is the time derivatives go away. And that's why they are steady. Right. So the time derivative goes away, and I'll write down the equations. Let's focus on R greater than R naught, where this Dirac delta doesn't matter. Which means everywhere outside the ghada, it's just simple convection at steady state. Can anyone tell me the solution to this equation, spherically symmetric solution to this equation? Does this equation seem familiar? This is a Laplace equation. So what's the spherically symmetric solution to this equation? Yes, 1 by r, exactly. So the steady state solution is very simple. We are of course doing it in 3D because if we did it in 2D, it would have been log r. So yeah, let's stick to 3D. But there is another fact. If you see t, I have wrote down 1 by r, which means that a very large r t goes to 0, which is not true at all. And the reason for that is a very far distance away from the ghada, we have the room temperature, which we have to balance. So we have to add that T room. So these are the steady state solutions. We still have Q now, which relates this gradient in temperature to gradient in the concentration. So we have a ratio of, we have a relation relating A and B, right? So let's do that. By the way, no one ever told me that the room is also not dry, because the room itself has some humidity content. So there is a rho out as well. But still, if you put this in this criteria, I'm just writing it down, you can do it by yourself. You will get A by B LD by kappa. Okay, that's great. I'll just replace either of A, let me replace B, A with B minus B LD by kappa. Right. And this is a steady state profile. So the question is, remember I have B by R. Sorry, this is not the right thing to write down. A by B, sorry, A by R and B by R. And B by A in this case will be minus LD by kappa. Right. So we can, what we can do is write down temperature, because A is related to B, temperature is now related to density. And temperature will be something like this. LD by kappa. Hoping I did the math correctly. No, I did not. T out. So by looking at the final temperature, we can guess what is the final vapor density is, or vice versa. If you can study the vapor density finally, there's a question. The color faint is too bad. Okay, never mind. Write down the final expression. Is this better? Yeah. Okay, great. So by looking at the final vapor density, I can study what is the final temperature will be. So, yes.
You can also mention at the wall how are rho and T going to be related in the steady state?
Yeah, at the wall rho and T are going to be related by this, the Q we derived. Okay, and
saturation vapor pressure.
Saturation vapor pressure. I won't write down the expression because it's a nonlinear expression, but you can look up how saturation vapor pressure is dependent in function of temperature, and you'll see it's a decreasing function. And therefore, you can see the final time steady state temperature as a function of steady state vapor density. So this is a demonstration, which this is a analysis that we did, which shows that you have two simple uncoupled equations, but the boundary condition can couple them, which is what Rama said. And this happens in everyday life. In any everyday problem you want to solve, there is a coupling in the boundary condition, even if there is no coupling in the ordinary differential equations or the partial differential equations you have. So I want to end this by showing you some profiles. So if you simulate the entire equation, the unsteady one, how temperature behaves, and let me do that on the projector by sharing screen. Yeah, yeah. Yes.
Since there is water vapor produced at the surface, shouldn't there be a delta function there also?
No.
Why not?
See, we are not considering anything inside the ghada.
So this is equation for outside, right?
Wall and outside.
Yeah.
So there is vapor everywhere, wall and outside. Yeah. And the fact is, you can't have a discontinuity in water vapor.
Density.
Yeah, you can't have a discontinuity. Initially you can, And that's, you can have it in an initial condition.
I mean, it's not discontinuous, differential is.
Maybe I can clarify one thing here. So like whenever you have something happening at a zero thickness interface, we're pretending that the ghada is zero thickness here. Whenever you have something injected there are two ways I can deal with that. One is I can put a source term like he's done in the temperature. Another is I can modify the boundary condition itself and not put any term in the equation. So that is what he's done for the former. So where he is actually going to change the rho at the wall, knowing the temperature, as he'll show you in the answer. So is that clear that you can do it either through the boundary condition or through the equation?
I can see that like from your statement, but I can't.
Yeah, you will see it when he shows. There is a source term in that, in the row also, because initially if I keep it in a dry, I've taken this ghada and kept it here, right? By the time we are sitting here, there is some water vapor which has reached, in fact, you and me when it's sitting there. And there is a source of water vapor there, but he's incorporated it by looking after, he's just taken the surface of that and he's put the, what should be the water vapor concentration there. And that will take care of the flux.
Okay, thanks.
Okay, right. Yeah, there is a question. Okay, I can't read it. Yeah. Why evaporating water first takes latent heat? Won't it first take specific heat before boiling point occurs and latent heat change? No. Okay, so if you keep a glass outside in a room and come back after 3 days, if you keep the glass open, you'll see a lot of water is gone. And that is because evaporation happens even at room temperature. So in any liquid, there are molecules, and you know molecules follow lattice-Boltzmann distribution. So there are some, not lattice-Boltzmann, sorry, Boltzmann distribution. So it follows a Boltzmann distribution. So there are some molecules which always have large enough velocity to spit out of the liquid and evaporate as vapor. That's what happens when you keep any liquid. So it doesn't need to go to 100 degrees centigrade before evaporating. I hope that answers your question. Any other questions? Oh, okay, I'll move.
He showed that we have two more.
Let me see if I can share my screen. Okay, Gobi, can you give me screen sharing permissions? I can't share screen. 1 second.
I will make me a co-host. Rashri. Yes.
Yeah. Great. So this is the temperature profile that you give. So this is not a representative time, and you shouldn't think of the time very much. Only the fact that the blue line was the initial profile, which is at 300 Kelvin. And after a long time, you see it slowly decreases, but the temperature far away from the ghada tries to stay the same, which is what's reasonable because temperature far away will stay the same. Whereas the plot for the rho becomes something like this. So as Jitendra, you were saying that there is a discontinuity. At the ghada, you can see the blue curve that was starting out has a discontinuity. But as you go on with time, the discontinuity vanishes because whatever is nearest to it, it will try to be the same concentration as that is in the surface. So temperature, initial temperature was a decreasing vapor density. And after some point, it tries to decrease even further and becomes saturated at a more or less flat thing. Of course, it can't get totally flat because then the evaporation will stop, and so the temperature will try to come back up, but more flatter than it usually is. So yeah, that's basically it. And yeah, you can try out solving the equations yourselves and with realistic values. It's a bit more challenging because you have to non-dimensionalize properly. You can't evaluate it every second. But yeah, this is the physics of it, of a really simple problem, but the physics is a bit difficult. Yeah.
I want to add a homework in this, like if you can tell whether it's good to keep the ghada in an AC room or out in the hot sun, which one will get you get you colder water.
Colder water as it comparatively to the environment or comparatively to the water itself? As it
Compared to the environment. Otherwise, it's easy for me to answer that in the AC, it won't reduce much. So I'm saying, like, can you come with conditions of under what AC, which one is better? So yeah, do that calculation yourself.
Still, I'm not getting the question.
The question
if I have to
is,
drink it, I will consider the cooler water, right? But if I have to consider your question, I mean, I think the temperature might, I mean, I'm just doing whatever is coming in my head.
okay, let's make the question very concrete.
Okay.
You have the outside temperature, let's say very hot, like 40 degrees, 38 degrees.
Yeah.
And you've kept the ghada there, it's all dry there.
Mm-hmm.
In the AC room, I've got like a temperature of, let's say, 20, let's make it comparable. So let's call it 30 degrees, although an AC room will not be 30. And I've started with the moisture in the room of 50%.
Okay.
So tell me whose final temperature will be lower.
Okay.
Yeah. The next experiment.
As it changes with, not that I know of. I mean, it can change slightly, but okay, no. It does, no? Because Vaishnavi, you said a latent hit amount, which was different from the latent hit I wrote down. It is different. Yeah, sorry. And the answer is reasonable, right? Because if you want to evaporate 1 gram of water at 100 degree, you have to give less heat than if you want to evaporate 1 gram of water at 10 degrees centigrade. Yeah. Okay. I don't know. Yeah. Yeah.
Experiment you may want to move in front. So, Ritvik, will you tell them when you want them to come forward?
Yeah, I think for the Vignal, they have to come forward.
Right now they can come?
Yeah. So I'll just say a few things about Vignal. A few things about
and then you'll ask.
Yeah. So first we'll demonstrate this Vignal instability. So this is basically when you drop.
Or you want to show it first and then tell, or tell and then show?
Okay, so I mean, I'll a few lines I will tell, then they can come. So we'll drop a blob of. Okay. Vignal instability. So basically what we'll do, we'll take a blob of ink and drop it in water. Now the moment you drop it, so from here, so it will drop like this. And because it is a fluid, this part will try to move in this way. This part will try to move in this way, right? So there is a circulation inside. Yeah. So there is a circulation inside the fluid. So you have a blob and there is circulations like this. So as it moves through the water, it tries to suck water in this direction. If it does that, then it tries to break into two, something like this. This circulation, this circulation. So you have a blob and the water is sucked inside from the middle. So it will form something like a donut shape. Something like this. Because the middle part is now water and side part is ink. So ideally, if I drop a water, I should first see a ring is forming. Then as it goes down, as Rama explained in the last class, the moment you have a ring inside a fluid moving, there are lots of instabilities. So it will not stay as a ring. It will start deforming. So instead of a ring, it starts to deform. since there is a deformation, it will try to break into smaller blobs. This parts will break into individual blobs. And again, this process will start again. So there is a cascade-like process which will go on, and you will see nice patterns. So we can start the experiment, then we can further discuss. Yeah, Jitendra. Yeah.
Instability which comes, which twists the vortex. Is it the same
I
instability?
mean, similar. So we have to zoom this one. Where is movie?
It's nice to see the real one, the screen one you can see in YouTube or something. That's why I wanted to come and see. Go ahead.
They can focus.
They can't focus, I think. So some people can come here also. Come on this side. No, we have to focus from here.
Please settle down. Huh? Don't move. Otherwise, it will keep vibrating.
Just don't stand in front of that.
Nobody breathes.
Yeah, don't. Wait a little more, like count till 100. Like a 2-minute silence.
Almost stable.
So this is an experiment you can do at home. You don't have to buy anything, get anything. You can drop any thing like this. The tiny clothes. So Avantika is saying when you're washing your clothes, if you squeeze it in water, if it's a color which runs, you can see the Vidnal instantly. So you don't even have to do Vidnal separate. Just wash clothes. Yeah. Oh, you mean for the blue? For oh yeah, like your school uniform, you could wear blue instead of white. There seems to be some.
Okay, first trial. Let's see if I can make the donut. Not perfect. Okay.
What happened? Yeah. Let's try again. Yeah. No, there's nothing else green. Wait.
I can't do it.
Can I do
Can you hold this? This will be fun.
Move that side.
Yeah. Just closer.
Equal. Do it from.
It's only the end blocks and nothing will happen if you get.
Closer to the surface.
Closer.
Closer to the surface. Yeah. Nice. Yes.
It's making a cascade of things. In that water shape.
Yeah.
And the camera is also.
This is 407 200 mm.
Yeah. This one is successful.
Yeah. Yeah.
Yeah, take the second.
Nice. Little bit from side.
The white clothes.
Yeah.
More at night.
Yeah, perfect. Perfect.
There is current missing. if you guys want to try. Yeah, now it's downstairs.
No. Yeah. We have two viscosities. Yes. Oh, yeah. Closer to the surface.
Questions for Pratik? Sorry, for Ritvik.
Yeah. Yeah, so we can just tell them to stay and
Oh, yeah, stay here.
Stay here.
You can come here also, Sam.
Yeah.
Otherwise, they can't show it on the camera.
Okay, let's move it. Or we can show it here only, this with mobile.
Mobile to चाहिए, put
Yeah.
it off view.
So this is pure water.
This is pure water, yeah.
This is desalted water, maybe 50-50%.
Yeah.
By volume.
Yeah, I will tell. Yeah, so everybody is here. Okay. So this is a demonstration of Faraday wave. So as you can see, this, look at the frequency, it is on 25 hertz. And if you touch this, you can feel it's vibrating. But if you look at the surface, there is not much movement. Okay, so just a second, decrease the amplitude. Just a second. Yeah.
Okay,
Yeah.
so maybe try not to touch this.
Yeah.
Yeah, otherwise it will absorb the vibration.
Yeah. So as you can see, this part is vibrating, but there is not much movement in the surface of the water. This is pure water mixed with dye. Now if I gradually, yeah.
Yeah, I just want to say that this is the simplest thing, like just a beaker kept on a vibrating table. That's all.
Yeah.
There's nothing like very difficult in this. And we've just colored it to make it visible.
Visible,
that's
yeah.
all.
Yeah. So now I gradually change the frequency. So now the frequency is 30 hertz. You can see very violent movement in the surface.
I think it's good if all of you go near.
Yeah, can you see the surface?
Take turns to go near and see from the top.
Now, yeah.
You can't see it at all in that screen.
Reduce amplitude. That's fine.
Sorry, online people, it doesn't look the same on the screen.
Now, if I further increase the frequency, see now the frequency is 41. Everything stopped. It's still vibrating, but any movement in the surface stopped completely. So this is a phenomena which is related to resonance. So very simply, if I try to explain this surface has some natural frequency. If I just perk up the surface, it will keep on vibrating. It will just vibrate. So there is a natural frequency. Now I am adding a forcing, time-dependent forcing, a periodic forcing from the boundary. So I have a natural frequency and there is a frequency of the driving force. The moment they are similar or they match, there is a resonance phenomena and the surface starts to vibrate. So this is very simply modeled using the driven harmonic oscillator. You can just write down a model for it using driven harmonic oscillator, but a little bit more complicated with the amplitude also. So the external driving, that also depends on the position that you don't have in normal harmonic oscillator. It's a bit complicated modeling. So this is known as Matthew equation. You can model it using Matthew equation. And it can be in principle exactly derived from the starting from Navier strokes. The derivation is a bit involved, but you can show this resonance phenomena by this model. Now, okay, so let me just try.
Did you tell about the wavelength?
Yeah. So now the vibration is only up and down. So that equation will not consider the exact patterns forming in the surface. It can only tell you what is the characteristic wavelength of the surface, the waves that appearing in the surface, what is the characteristic wavelength of that. If you look at it, you can see, okay, there is some characteristic length in the motion. Just let me reduce the amplitude. Yeah. If you look at it, can you identify there are some particular length scale which is waves up from particular length scale is appearing in the surface. So, but the problem is if you just increase the amplitude too much, it can't be modeled using Matthew equation. You can't write down the simple model. So if I increase the amplitude too much, it goes to turbulence. Now you see it's completely random motion. So actually you can write a simple linear scaling with how much amplitude you are increasing and how much fraction is chaotic, and it follows a nice power law. So more the amplitude, more the chaotic behavior. So this Matthew equation description is for very small amplitude. So now you can't see any characteristic length. Everything is very chaotic. But if you look at very low wavelength, very low amplitude. Here, now see. Here things are more regular and a particular length scale is appearing. Yeah. Now I go to turbulence again. So there is super complicated things going on.
What is on the surface of the liquid again?
This is tracer PIV particles, just to see the how chaotic it is. Probably that Iqbal, it is polystyrene beads?
No, this is PIV, some amine beads. Polyamide.
But I think if you put talcum powder also, you'll see something on the surface.
So this resonance frequency is the characteristics of the fluid itself?
Yeah, so it depends on the surface tension of the fluid. It depends on the viscosity of the fluid.
So it can characterize.
Yes, and we have a higher we have a fluid with higher viscosity. If we just change the fluid, the wavelength will change. The characteristic wavelength will change. That will also demonstrate.
So the resonance frequency has nothing to do with the shape of the cylinder.
No, nothing.
And we can do with sand as well, can we?
Yes, that is another class of problem. You have a vibrating plate and you put sands. That is essentially the same kind of phenomena. It's more complicated because there is fluid.
But that's also very beautiful.
Yeah. Right? I mean, essentially, those are also called Faraday waves.
Okay. We can see a music video at the end of it, right? There's this music artist which works with it, and in his music video, that's just water doing something amazing.
And also, you can just say, look at this frequency; it's very sharp. I mean, it's 30. If I just increase a little bit, everything gone. Because it crosses the resonant frequency range. So there is a peak at a particular frequency. Around that, you have some visible motion of the surface. Once it crosses that range, you see nothing. Once you go below the range, there is nothing. Just like a resonance phenomena. So,
what's the frequency dependent on?
Frequency dependent?
What is it dependent on?
This is the external philosophy.
No.
Okay. That's depend on the fluid itself, the surface.
So that, like the length of the fluid.
Natural. Okay, so that depends mainly on the natural frequency of the vibration, and that natural frequency depends on surface tension, viscosity.
You'll be writing that down, no?
Dispersion equation is a bit complicated. I can write down the equation. Yeah. So for the very.
That's the important thing. How the wave, the length scale, there are spatial patterns which are coming out of nowhere.
Yeah. So
you'll be writing the scaling for that.
Yeah. So the for very low viscosity, you can write down you can just ignore the viscosity. You can write down a good dispersion relation. For viscosity, it modifies to a very complicated relation. I will write down the ideal one.
Is this the same patterns we'll be observing in the bulk of the fluid?
No,
as well?
This is surface phenomena. This is the surface.
And now since the perturbation is global rather than a point like or localized, what would Yeah, since the perturbation is global rather than a point like a very point source, how would you expect the waves to be had it been otherwise? What if you had one point very other?
Okay, so this setup is not, I mean, we can't modify this setup because there is this rigid boundary in the bottom. So if you just vibrate one point, it will just, so whole bottom plate is vibrating then. So
okay,
how do you
just,
how do you
hypothetical situation?
Okay.
If I were to just vibrate, let's say around x equal to 0 or something.
Okay, so how do you include that? I mean,
How
you
do
put
you-
something in the fluid or?
I just tap.
Oh, so that is a perturbation, right?
Yeah.
That is a perturbation. Then it will vibrate with natural frequency, determined by the viscosity, surface tension, and all.
And that wouldn't be a Faraday wave.
No, because you start a vibration, then you will left the system alone, right? So, or you are continuously forcing.
Let's say I'm forcing it.
Okay, how? Because
I have a tuning fork or something.
tuning fork. Okay, so okay, that will, I guess, will create only ripples.
So there won't be any.
I think not. Okay, so now you can see very nice stable patterns if you look at it. Super stable patterns, and this is the characteristic length scale. So these particles are accumulated at the valleys of the structures.
By the way, if you put non-Newtonian fluid, something different will occur, right?
Yeah, completely.
It's like if I have put curd on it,
Curd,
not like in
curd.
a bowl, and there's a very different kind of phenomenon.
It
It's
should.
spooky, actually.
It should.
So what happens there?
I don't know. For Newtonian fluid, non-Newtonian fluids, things are very counterintuitive.
And these phenomena, like these equations won't work there.
At least the Matthew equation will not work definitely.
Do we have some equations which work on that?
I don't. I have to look it up.
Is it like more dense fluids have a higher resonant frequency?
So will be going towards non-Newtonian, I think.
It will require more energy, so high.
No, so frequency has nothing to do with. Okay, so maybe it's the amplitude, resonant frequency. For you're asking with a higher viscosity, do we need more frequency? I think it's less. Probably we can check. Maybe it's less.
What is
Probably
happening in
less.
the bulk of the fluid at this point? I mean,
Visibly not something.
you can't see it right
Yeah,
now,
yeah.
But I mean, what if you have a clear liquid and you drop the
PIV particles inside the liquid.
or just ink for that matter?
Inside.
Huh.
This particles is too much, that's why they can't see. Can we spoon it out?
Spoon, yeah.
Do you have a spoon or
yeah.
something? Let us suck them out.
Will that work?
No, probably no.
Spoon चाहिए.
Yeah, we will need something. I think a paper might work as well.
Yeah, the bulk part is, I don't have any right way answer for the bulk part. But this is,
Definitely they are vibrating.
yeah, but.
Can be determined exactly.
More surface area. Yeah.
For bulk, I mean, you have to go to full Navier strokes because so the surface, it reduces to the Matthew equation from starting from Navier strokes. You can show that. You can write down the amplitude equation, it goes to the Matthew equation exactly. And there are considerations that the length scale in the surface should be very, very less than the depth of the fluid. That why you can make many approximation and reduce it to Matthew equation.
So if you have a very thin.
No, that's not at all valid. Not at all valid.
So this frequency is not dependent on the shape.
Yeah,
of
now
the
make it vibrate.
bowl
Let's see
or
if we
the
can
height.
see the surface pattern.
You need a little bit more frequency.
So note the frequency so that
Yeah.
when it changes the fluid, you'll
Yeah,
see
yeah.
the difference.
This is around 30.
And note the pattern.
And
Do you
let me
see the
reduce.
surface pattern? What's the wavelength? Estimate.
1 mm.
Wavelength, Appa.
Oh.
Distance between two peaks.
Yeah.
Two peaks, what do you think?
Order of a centimeter.
Yeah, because Scott.
Yeah, closer to a centimeter, maybe. Like, but less than a centimeter. Right? It's like this one. Anyway, at least keep a visual memory of it so that you can compare it against the next.
Niche from the bottom, we are putting the vibration. You can just touch and feel it. नीचे से vibrate हो रहा है, and the moment it matches the natural frequency of the surface, resonance occurs. Because the surface, you think there's a stable surface, it will be a little perturbation. What it will do? It will do some oscillation. So there, exactly. So there is a natural frequency.
It's basically
vertical vibration of the entire volume.
No, it's at the surface. Yeah, bulk means something is going on which these equations don't capture.
The force you're getting from
which
is coming through the
through the bulk.
और ये लेंस स्केल्स जो क्रिएट हो रहे हैं वो कैसे
Those length scales, they depend on the natural this viscosity, surface tension, everything, and very complicated way they scale with. Which frequency? Resonant. Yeah, they also depend on these things.
So, but then it should not depend on the length.
No length.
Doesn't
No.
the wine glass experiment.
No, I'm just thinking how the
length is, I mean, the equations that we wrote for this, ideally the length is infinite, very long, such that you can do many approximations.
But the diameter should matter, right?
Diameter shouldn't matter.
Should not.
No, because I mean,
It's still that's
Yeah.
anywhere.
Yeah.
But if you're at the edge, then it's different.
I mean, at edge things will be different, but we'll be looking at the bulk. Things are, I mean, bulk of the surface.
But it
Things-
doesn't look different at the edge.
Yeah, that's strange.
Then you can see something there, but not the pattern.
What if you put a thin layer of oil or something on top?
There will be waves, but this no longer.
The
this-
shapes, all of that will be different.
Everything will be
Frequency
different. Everything.
What is this frequency? 40.
So this is 30. 30 hertz.
If you do double of it, also you'll see it.
No. You can try.
You can change it now.
Yeah.
Discuss.
Yeah.
Try it. I'll try it.
Yeah, try.
But there's still imaging.
Donut shape becomes honeycomb.
Okay. There is multiple instabilities. The one is the Rama talk pro instability. There's many instabilities coming. So it can be shown that if a vortex moving through a fluid is not a stable shape, like the smoke rings and all, and not stable. So eventually they will break out into this. The mechanism for this, you have to write down amplitude equation and see one by one many modes become unstable. So circle is the first mode. So it's very smooth figure. The moment it goes to this equation, that means a smaller length scale is created in the problem. That means the higher modes are getting excited. That you have to figure out by looking at the amplitude equation, and then not straightforward actually.
So if we have a more viscous liquid like stability, instability,
Stability actually generally increases for viscous. So it doesn't have enough room to move.
can we freeze it in donut shape?
Yeah. Will the resonance frequency change? Will the resonance frequency change? Yeah, so the resonance frequency will change with temperature, but the effect will be very small. So it will change because temperature affects the viscosity and the surface tension. As a result, the resonant frequency will change, but that effect will be very small unless you are going to vary temperature unless you are considering huge variations in temperature. Does that? Yeah, that frequency depends on gravity, correct. Which one? This is the more viscous. Yeah. Yeah. So the frequency, who was asking the frequency wala thing? Viscosity, yeah, it's less for high viscosity. And what about the characteristic length? What do you think? More. Yes. Yes, that's true. Not decreasing. Increased. Wavelength increased. Yeah, and the wavelength increased. Yeah, clearly the wavelength increased.
Oh, it came?
Yeah.
Yes, no? I'll just see if it came. Can you, do you agree that the wavelength has increased? Yes. Those little hexagons have become bigger, no? To smaller hexagons.
And now you can try with increasing the amplitude. You can see more chaotic things going on. Oh, maybe because the fluid is more viscous, you don't see the chaos that much.
You won't. This will be like
Less turbulent.
Reynolds
is yeah, smaller here.
You can come and play with it yourself.
So if you put honey.
Yeah.
Now you can see it nicely.
That is a new height. We should try this.
We will try this.
Faraday. See, there is not much turbulence.
Anything is happening or not.
Viscosity increase ho gaya.
No, the problem is if you make it too much more viscous, our machine doesn't go down to those frequencies. It's already hitting minimum frequency here.
Yeah.
So like you need a different machine.
Not here, but we can change.
Yeah, you can have a machine with a lower vibration rate and a very viscous fluid. Yeah, we can try it.
Very viscous means less frequency you need.
But amplitude
yeah, otherwise it will not move at all.
Gravity ko overcome.
So there is two effects: gravity.
We can.
So we can do the experiment.
Plus surface tension and viscosity combined.
We can do that.
We can do that.
That decides the natural frequency.
So we will do it. I don't know when, but we can do it. So we will do it.
We have wax in the lab. So you're welcome to come and play.
So generally what we
You're welcome to come and set it up.
When we write the linear equation, we actually neglect the amplitude. So we say the amplitude is very less compared to the height. So we just write down a linear equation.
We can do multiple experiments that way. Like, even that one, the first one we did.
Yeah.
Okay. Then. Hi, I have one.
Why higher?
He will tell you. He's asking some question. Maybe show it on the board.
Why higher viscosity have lower resonance?
Okay. So
show it on the board like
for viscosity, yes, too complicated.
But just show how it scales dimensionally.
Viscosity.
I said like do a dimensional analysis.
But that's just not, I think, suitable for this. The scaling is very different. I mean, the dispersion relation.
Oh.
Not.
Okay, just explain how the dispersion relation comes about.
Yeah. So one thing is more.
Maybe we can have everybody sit down again.
No, they can just
show it on the board.
Yeah, they can try. So.
They can be trying. You can talk
On
the board.
Yeah.
The online people will get bored otherwise.
Okay.
So just explain.
Yeah. So what you're asking, with higher viscosity?
Lower resonance.
Yeah.
So you can answer it loudly so that the people online also can hear the question and the answer.
Mm-hmm. Yeah. So, I don't think how to explain this. I mean, simply.
Due to the cohesion between the molecules is more.
Not that only, because it's related to the
Another 5 minutes or so we can.
Yeah. When it happens. Yeah, I've just read.
But what if we use a more viscous fluid for this vibrating?
The resonant frequency will go down.
Okay, it will go down.
It will go down. And the thing is, the problem is this: how the natural frequency scales with the viscosity is a very complicated relation. So generally, the calculation they consider two fluids. One with viscosity in U1, another is because we have air now. So we have essentially two fluid, and the interface is vibrating. So we have a very complicated looking equation, and I mean this is very complicated. I can show you the equation.
So in the vacuum, the results will be different.
Yeah, but I mean This is.
It is similar to the concepts of the resonance.
Higher viscosity,
the bridges, how they resonate.
Yes. Essentially, the idea is same, but I will show you the relation. It's super complicated. That's why I don't want to write it. So the dispersion relation goes like this. So these two densities are the two densities of different fluids.
Like here for water and air.
Here and eta 1, eta 2 are two different. These are the this is how this is the dispersion relation looks like.
Omega is frequency.
And that's also quite approximated.
P2.
Yeah.
P2 is
Not exactly approximate.
P2 is air.
P2 is air. The rho 1 is, I think rho 1 is the fluid, rho 2 is the air.
So in vacuum, the frequency will increase.
Yeah. In vacuum, the frequency will increase. No, not vacuum.
P2 if we put
no. There is density, na. There is also density. Where is it?
I had one question.
Yeah.
So the resonance of the fluid is also, so even solid bodies have resonant frequency.
Yeah.
So the 30 hertz is the resonance of the beaker plus the fluid.
Here the beaker is not important because it happens irrespective of any geometry.
Irrespective of the resonant frequency of the beaker?
Of the beaker,
the
correct.
resonance of the water will be 30 hertz.
Exactly. So the resonant frequency depends only, it's a pure property of the surface. Okay. So think of simply, you have a beaker, you perturb the surface, you just push it somehow. What will happen? The water will move up and down, and then finally settle. That is the natural frequency.
Okay.
And if you take a round beaker and a cubical beaker, there might be a slight difference because of the boundary effect, but there will be not much difference.
Okay, so now Ritvik will just give you a short explanation and we'll break for lunch. We are meeting at 2 o'clock, and where is that? Where is Iqbal? We are meeting at 2 o'clock in the JC Bose lab.